involuted association. This is a fancy way of saying a table that refers back to itself. Okay, so what we've got here is a table representing all the employees of an organisation. And every employee is a person, so there's a reference to a person table. And then we have this involuted association that every staff member has to have a manager, and actually it says staff members don't have to have a manager. Okay. So not every staff member, you can have multiples, right? And every manager, I'm reading it the wrong way around, sorry. Every manager manages any number of staff, and it can manage 0 staff. I don't know why they would be a manager if they manage 0 staff, right? And every staff member has exactly 1 manager. So that's the way to read it. So this type of association is not uncommon, particularly with people, right? So employment relationships, staff-student relationships. Sometimes you can have staff who are also students, right? Marriage is another example. Family relationships in general. It is very difficult to handle, particularly if you have many-to-many relationships in table form. So what we do is introduce another table in cases like this to get rid of that direct reference backwards. Okay, so we've got another table here which just has references into the employee table for the manager and the employer ID. Okay? And the two of those things together becomes the primary key for this table. Okay, so it simplifies that association rather than having the direct link backwards. Another type of association that can be problematic is what's known as a ternary association. Okay, so here, every student is associated with a degree program and a department. And every degree program is also associated with a department. Right? So registration is ternary, relating those 3 things. And we've got multiplicities at each end, but fixed instances. For any given student, there's going to be a particular thing. Right? So to get rid of that, what do you think we do?
We merge 2 tables?
No, we add another table again. Okay, so it's a concept known as registration that creates that link between the 3 things. So we create a table for registration, right, which keeps separate these 3 tables and combines them here. Now notice here that the registration number and the course ID become the primary keys because the department ID is a dependent thing based upon those 2. Okay, so given a particular student in a particular course, that is going to define what department they fall into. We don't need to use that as part of the primary key, the department. We can We'll go one step further though. So having recognised that that department arises from the other two, we can make it binary rather than ternary. Okay? So what we've done here is we've said for any given student, they're associated with a particular degree. For any given degree, we have one or more students, which makes up the cohort. For any given degree, we have a home department, right? And for any given department, we have however many students. Right? So this is just going one step further from the previous slide. But notice here, we've got a redundant path. Because this red line here and this blue line here can both reach the department. So for any given student, yeah, they're associated with the department, but we can work out what department they're associated with by going through which degree they're doing. So because we can determine which department they're in, associated by going through which degree they're in, we can eliminate that redundant path. And we always keep the longer path and delete the shorter path.
Why we delete the short term?
Okay, because we want to know what degree, what department a degree is associated with. If we deleted this path, we wouldn't have a route to that information. Okay? Because we only had a path from student to department. We delete that shorter path, we would have no way of knowing which department a degree was associated with.
Can we keep it linked between the student and degree and the student with department? So we have two parts of the student.
And if the student is doing 2 degrees, okay, so I don't think you can do combined degrees at this institution, but at some institutions you can undertake a combined degree.
At the same time?
At the same time. So where I studied at the University of Melbourne, it was very common to do a combined degree in engineering and commerce, for example. So you were enrolled in both at the same time, and you came out with a joint degree at the end. So you were associated with 2 separate, faculties in that case, and 2 separate degree programs. Okay, so we've looked at some examples of how we would want to transform tables. Let's sort of look at it a bit more formally now. So the idea is we start with an arbitrary table and then we subdivide it. Right? So we might start with all of our data in one table, maybe with columns that have lists in some of them. Right? So for example, for a student, you'd have their UCard, their registration ID, their name, their address, their degree program, their year of study, the modules that they're studying. So there's an example of a list, because there would be multiple items in that particular column, and so on. The next step is to actually break up those lists by replicating the atomic answer in data in many rows. So take that item that has appeared as a list in the table, create a new table for that thing, and then the student will appear multiple times in that new table. Splitting up into many tables to remove replicated data, and making sure that non-key attributes depend fully on the key. Why do you want to do that? Last point there. Okay, so if we've got the primary key, and then we've got other information stored in the table. If that other information isn't dependent upon the key, it means that we haven't got something that's going to uniquely look up the thing that we want. Right? So that's the reason why we want it to be fully dependent. Okay, because the idea is the key is the thing that's going to find the information that we want. If the information that we want depends upon something other than the key, we're not necessarily going to get the thing that we want by using that key. Okay, so it's driven by the functional dependency in the data. So for example, the customer's name or age depend upon which customer we're talking about, right? So there's a functional dependency, right? So we say the customer ID gives you the customer name, the customer ID gives you the customer age, but we don't say that the customer age gives you the customer name or the customer name gives you the customer age, because we might have multiple same names, yeah? You can have transitive relationships. So like in that previous example we had, the department ID is dependent upon the registration number, but only via the degree, right? You can have partial dependencies. Okay, so you can have a relationship which says the module ID is a partial dependency to the lecturer. A lecturer ID is going to have some relationship between the module ID and the registration number, because there might be different instances of the module ID which are associated with different lecturers, right? So not so common for the degrees that you're studying, but for degrees with very large cohorts, they might be split into different lecture streams, each having a different lecturer. Okay, so they'll have the same module content, but delivered by a different person. And you might have multi-valued things, like a company having product sets, different product sets. Okay, so you might have product sets for one company producing take Toshiba, produce laptops, produce phones, and within each of those things there are different product sets. Yeah. Okay, so I talked about these normal forms. We have this idea of first normal form, which has got rid of the lists or repeating data groups and has a primary key for each row. So it's the simplest form of a properly constructed table, but it's not a particularly efficient form for a database. Okay, so it works. It will allow you to look things up and store things and get things properly, but it's not necessarily a good representation. And basically as we go down this list, everything above it is still true, and then we add extra constraints upon the database. So in second normal form, no non-key attributes depend on part of a compound primary key. So we have full functional dependence on a key. Third third normal form is what we're aiming for, right? No non-key attributes depend upon other non-key attributes. So you don't have transitive dependencies on the primary key. Right, so we're keeping things as disjoint as possible, essentially. And then there's this sort of variant on this called, generally just called BCNF, or voice cog normal form, where every attribute on which other attributes fully depend is a candidate key, right? Fourth normal form and fifth normal form are really just for researchers. Okay, so don't worry about those ones. Okay, so first normal form. So here's where you might start with your things that contain lists. But when we're constructing a database, remember we want fixed width fields, and so we don't want lists of items that can be variable length in there. So what we do instead is we take that thing that has lists and we create separate items for each of them. So for every registration number, there might be multiple entries in the table, right? So here we have representing each of those things in the list. So that's the transformation into first normal form. Okay, so now we have a table where everything is a fixed width. So that is kind of like the minimum database that you can implement, but not necessarily the best representation for it. Second normal form. So we've got an examinations table, which is in first normal form, right? Each item in the table has the registration number and module ID as the primary key. So those two things together should give you something unique. For any registration number and module ID, there's going to be a lecturer associated with it and the marks that they received. Okay, but they might have the same lecturer for different modules. They might have the same marks for different modules. They're independent things, but they're not really closely related together. So what we're doing here is we're going to say, okay, so we're going to split those things up. And we're going to say the marks are associated with the registration number and the module ID. The lecturer doesn't really matter. Okay, it is going to be a particular lecturer assigning the mark, but the thing that we're interested in this table is just these two being the key and this being the value that we want to find. And then a separate table for who teaches which module, right? Where the module ID is the key and the lecturer is an independent thing. Now this is a case where we're assuming that there aren't multiple instances of the same module with different modules. Okay, so it's going to depend on your use case, how you do the splitting. Okay, registration. This one's in second normal form. So we've got the registration ID, the degree ID, and the department ID. Each degree taken depends directly on the student registration number. The home department ID depends on the degree ID and only indirectly on the primary key, which is the student registration number, right? So we eliminate those transitive dependencies from the table by splitting it into two tables. So we have the registration. For any registration number, we have a particular degree ID. And then we have the owner of a degree in a separate table where the key is the degree ID and the value is the department ID. So we no longer have a table with transitive dependencies in it. Right? Transitive dependency was that link across there. I said fourth normal form and fifth normal form were really for researchers, but let's just look at an example of fourth normal form. Okay, so here we've got a table called cells, and we've got every field within this table is part of the primary key. The company, the product, and the country. We've got a multi-valued dependency. A set of products and a set of countries depend upon the company, but they're independent of each other. So the company exports to particular countries, and the company produces particular products. Right? And every company that exports to a particular company offers its products in that country, and every company that produces particular products exports to particular countries. So they're split into separate tables. Okay, but that generally you don't need to go that far. You will get better performance the further you push it along the normal form list, so to speak. But third normal form is generally good enough. Okay? So as I said, we want to aim for at least third normal form, basically looking for a good separation of data. That's the key thing, is not trying to avoid lots of dependencies is the big thing. Yeah. Things to check. So, do you have instances where you have what's known as an insertion anomaly, where you can't insert X until you know what some other value is? Right? So, if I want to insert something to the database, is there information that I need to know before I can put it into that table that I don't know yet? That's an insertion anomaly. And it's probably an indication that things need to be split. Because if those things are in two separate tables, then you can insert the one thing and then insert the other, rather than trying to have to gather the information first. An update anomaly that affects some but not all rows, where you want to change something and it's having flow-on effects throughout your table. There's something wrong with your design then, probably. And a deletion anomaly, where deleting a particular row in your table loses some other information that you really wanted to retain. There's another indication that they probably should be in separate tables. Right? But sometimes you want to do what we call denormalization. So going from third or fourth normal form back towards first normal form. The reason that you want to do that is that it can make searching more efficient. So if we have to look up lots of different tables when we do our search, that slows down the searches, right? And it also means that we have, in a highly normalized form, we're going to have lots of tables, right? And that leads to data fragmentation. Data fragmentation can slow things down as well, because you're getting bits from all different parts of the physical device in terms of storage, and it's only milliseconds. But if you're doing lots and lots of lookups and stores and so on, those milliseconds do add up surprisingly much, and it can make an impact. So if you're really interested in efficiency, sometimes denormalization can help. Right? Yes?
So what's the point of the normalization if we didn't get that efficiency?
What's the point of the normalization? Yeah, so the normalization is about maintaining your data in a consistent state efficiently. So ensuring that you don't have duplication, right? So if a customer updates their address, it gets updated in one table, and it doesn't accidentally forget that there was another table that also contains the address that had to be updated. So keeping the address in two separate places would be a bad thing. But if we don't design our database properly, that can happen, right? Where you have duplication of data and you need to make sure that it's updated everywhere at the same time. But it's more about these sorts of things. So if we denormalize, we can end up with these sorts of issues where you delete some information, a row from your table, because you no longer, so you say you stopped manufacturing a particular product, and so you don't want it in your product database anymore. So you delete the row on the table that was associated with that product. But that might accidentally delete information about spare parts available for that product if you have denormalized it, because you would have everything in the same row at that table about not just the product itself, but the part numbers associated with it and all that sort of thing. And so deleting the product from your database just deletes everything to do with that product if it's denormalized. But if it's in separate tables, you'd have one table for your current products, and you'd have another table for your supported products, and another table perhaps for your unsupported products, that type of thing. Okay. Generalization issues. How many tables do you think you need to store this information? So for any person, they can be a student, they can be a lecturer. But any particular student is just one person, any particular lecturer is just one person. At the moment, it's described as 3 separate tables. Here we've got an added notation which basically gives a constraint on a relationship, and here we're saying that it's overlapping, saying that a student can be both, sorry, a person can be both a student and a lecturer. Okay? So some lecturers might be currently undertaking a PhD, for example, or studying for an advanced diploma in education, that type of thing. Or they might just be doing a language in addition to their thing. So if a student can be, if a person can be both a student and a lecturer, then you have to have all 3 tables in the database. Okay? So we have the person table, the student table, and the lecturer table. And if though, rather than overlapping, we have disjoint, so a person can only be a student or a lecturer, but not both at the same time, only need 2 tables. Because we're never going to have a person who is both a student and a lecturer. They're uniquely different things. Okay, so we no longer need the person thing. If we were going to denormalize it though, we could roll them both back into the person, where we have the registration, student registration number, and the degree ID, and the employer number, and the office as fields within that person thing, and some of them could be null. And this would work for either form. Right, so it could work if you were saying it was disjoint, where you have to have null in either one of those two, or it could work where you were allowing them to be both. Right? So it reduces the number of joins between tables when you want to construct the person, because we had at the high, when we were having the overlapping thing where a person could be both a student and a lecturer, we had to have 3 separate tables. So it reduces the number of joins because we don't have to make the links between the different tables. But it's wasteful in terms of space because you're going to have lots of null fields. The number of times when you have somebody who is both a lecturer and a student is relatively small in the big scope of things. There's vastly many more people who are either a lecturer or a student, but not both. So we're going to have lots and lots of null fields, and it's only going to be satisfying 2NF because of the transitive dependency between registration number and employee number. Okay, so the basic idea with denormalization, though, should you want to do it, is to reduce the number of tables. Right? So flatten that generalization into one table, but generally it means wasted space. You might replicate part data in the table, so again you're wasting space, but it does save on reconstructing objects. Okay, you optimize access paths, you retain redundant access paths through the data, but again you've got additional foreign keys and a risk of inconsistency. Okay, it does save time when searching. But I think what you'll find is that most modern day databases use highly sophisticated techniques to avoid denormalization. Go for a higher normal form, but use other techniques to speed things up. Right? So, in summary, the evolution of databases meant that it moved from a network model, just sort of having hierarchies of data, so to speak, through to the relational model, which is the modern form of databases. We store the data in the tables where the rows denote individual objects and the columns denote their simple attributes, so much more simple than an object in a computer program. You have to be able to identify each row uniquely by a primary key. If you have duplicate primary keys in your database, there is something wrong with it. Right? It shouldn't be possible for that to happen. Navigation is one direction, from the many to one, using a foreign key to identify the related row in another table. And we're aiming for data to be normalized to third normal form or fourth normal form to support insert, update, and delete without duplication or cascading effects. That's why we're going for that form. The entity relationship modeling is one approach to normalizing normalizing data based on optimizing the multiplicities. Now, if you want to look at another approach to normalization, as I said, look at the appendix here in these slides, or read the textbooks that were referred at the start. Traditional table normalization is what's covered in the appendix. Okay, so the work for this week. Practical exercise. We have grocers, good news grocers. They've got two lots of data. The first view is the price list. Right? So we've got, in that table, we've got the department, product code, aisle number, price, and the unit of measure that they're using. Okay, I will remember, I promised, I only realised yesterday that somebody emailed me that I didn't put up the questions from last week. Please tell me when I do something like that. Right? As soon as I go back to my office, though, I'll do it today. Right? The second view is the product cost report. Okay, so we've got the supplier, the product, the cost, the markup that's applied to it, the price that results, and the department code. Okay, so the challenge is, first of all, for each of these views, separately, design databases to represent these views. Right? So you'll get two sets of tables, one for the first view, one for the second. Then, bearing in mind that this is related data used by these grocers, so these are just two different views that the grocer takes upon their data, can we combine the tables that were produced from those two views to give us a single database that captures both views? Okay, so I'm going to let you think about that in your own time. Does anybody have any questions about what's required here? Okay, if after you start thinking about it, you have questions, email me. What I would like to talk about, though, are these two discussion problems, which we have already had some discussion on. But first of all, what is the advantage of higher levels of normalization? Increase the number of tables.
Avoid redundancy.
Avoid redundancy, yes. Yeah, so yeah, higher number of tables is actually a disadvantage. So higher levels of normalization does lead to more tables, but more tables isn't an advantage in itself. It produces this advantage, though, that you avoid redundancy. Okay? That's one of the advantages. There's another one.
Reduce null's value.
Sorry?
Reduce null's value. Save memory space.
Save memory space. So yes, so there's less null values. That's what you're saying. Yeah. Okay. So there are fewer places, or there should in fact be no places where you have empty information in your tables. Right. So the idea is that for every item in your table, there will be a value. That you won't have any items in your table that have null values in some of your columns.
If we have null value, we will delete it?
Yeah, basically, if you've got a high form of normalization, then every row in your table, there should be a unique value for it. And so if there is a null item in your table, that just means you've got no information about that thing, so yes, you would delete it. It would be there'd be no point having it there anymore. Yes?
update all date types, something changed? I mean, if something changed.
Yeah, so you'll have no indirect dependencies anymore, which means that when you do an update, you will anything related to it will receive that update essentially. Okay, this is related to the no redundancies. It's kind of like the flip side to the no redundancies, if you want. Yeah. Okay, so in contrast to that, why might you want to denormalize a database?
It can speed the search process up.
Yeah, so the big one is in speeding up the search process. Anything else? Why does it speed up the search process?
Because we don't need to jump from one table to another and search.
Yeah, so each time you access a table, you have to load information into memory and you have to search through that table and find the thing. And if you're having to look up 3 or 4 different tables to get the complete set of data that you want, that's 3 or 4 separate lookups, right? So every time you load the load the table. If you have it all in one table instead of in 3 or 4 different tables, or 9 or 10 different, however many, yes, your table itself is going to be bigger, but doing the load in the first place will take a bit longer, but not as long as doing n different loads. Okay, so it's about the way that data is transferred from storage into memory and that sort of thing. Okay, so once again, we're doing very theoretical things here. So previous exercise, I have asked you to design the tables for your database, right? But I haven't said anything about how you would actually implement your database yet, right? And I don't think that's anything you're doing in other modules this semester, is it?
Yeah.
No.
Is that a yes, you agree with me, or you are doing it somewhere else? Okay.
We
So
don't have databases.
you don't have databases, no. So as far as I'm aware, the first time that you will be doing the implementation of databases is in my module next semester, where we do the practical application of the software engineering project, right? At the same time, I believe that you're going to be doing it in another module, but timing-wise, I'm not sure whether you'll cover it first with me or with the other module, okay? The point, though, is that the challenging part of the software engineering side of databases is getting the tables right, and that's independent on how you implement it, okay? So just like we talked about last week, how architectural design is something that you want to get right, because refactoring your architectural design is a really difficult thing, because it affects all parts of your system and you have to change everything if you change your architecture. The database underlying your system is a really core part of the architecture, right? So getting your database right from the start will save you massive amounts of time. So thinking about the correct form for your tables and the relationships between your tables and that sort of thing, and making sure you don't have redundancies and dependencies and that type of thing is really, really important in your design, and completely independent of the practical implementation of how you implement that database. Okay, so it's perfectly fine and legitimate to be talking about it in these abstract terms about what are the tables going to look like, right? The practicalities of how you implement it are kind of a minor detail. And you'll have the same, when you do your software project next semester, that will certainly be true. So you should be thinking about what your tables look like long before you start thinking about how you're going to actually implement that. Right? Okay.